How we doing, guys? We're going to get going today on our second lecture in the ecology unit. As I mentioned in the first lecture, today's lecture is going to focus on the biosphere and specific systems in the biosphere regarding climate. So we have something called the global climate system, which is one of the interacting systems within the biosphere that helps determine things like weather. So we're going to look today at what is weather and what is climate and what are the differences between them. But not only that, but how do those things form? What factors are at play that give us the temperature and the precipitation that we live with on a day-to-day basis? So, to start with, climate is defined by the patterns and the average temperatures, precipitations, wind, and cloud over a long period of time. So, over many years, we see patterns of things like temperature. We see patterns of the amount of precipitation, the strength of winds, and the amount of clouds in a given area over a given amount of time. That is what we refer to as climate. It's something that's predictable. It's something that we have come to expect, and it's something that you're typically not surprised by, is a good way to think of it. So, for example, you wouldn't be surprised if it was cool and rainy in Seattle, or if it was warm in Miami. Those are things that we have come to understand as patterns in those areas, so that is a part of their climate. Weather, on the other hand, consists of short-term changes in those same factors. So again, you're working with temperature, precipitation, clouds, and wind, but this time it's more short-term. It's from a day-to-day or minute-to-minute basis. So weather can be difficult to predict. We all know that we attempt to predict weather. You've got an app on your phone that tells you what the prediction of the weather is going to be for the week. You've got weathermen. If you watch the news, weathermen get joked about a lot because it's difficult to predict weather. But we sure do give it a shot. So that's just sort of the general differences or similarities between weather and climate. But how do those things form? Where do they come from? How do we get the weather or the climate? So both weather and climate are produced by a global system of winds. Yes, within our globe, within the biosphere, there is a system of predictable wind patterns. There's also a predictable ocean current, and those things both work together to produce both climate and weather. This is the global climate system. Okay, so from the basis, its core is shaped and powered by the total amount of solar energy in the biosphere. It's also impacted by the unequal distribution of heat between the poles and the equator. So what do we mean by that? First of all, how is solar energy kept within the biosphere? And secondly, why is there an unequal distribution of heat around the globe? And then finally, how does heat ultimately impact things like wind and ocean currents? Okay, you don't think of typically like, oh, it's a hot day today, man, that's got a big impact on the wind. But in fact, what we see globally in this system is that the amount of solar radiation that we get from the sun has a great impact on wind and ocean currents, which in turn globally determine climates. So let's look into that system. First and foremost, the way that we trap that heat is through the greenhouse effect. So this process is the way that we get the temperature on Earth that we have. So it's a process that we have where certain gases in the atmosphere that we have coined greenhouse gases work to trap sunlight in the Earth's atmosphere, and they trap it as heat. So what you see happening is that some energy from the sun is reflected into space, and some energy is absorbed and converted into heat. So in turn, some of that heat is re-radiated into space. But some of that heat that's being re-radiated is trapped within the atmosphere. And the Earth's temperature is determined by the balance of heat that stays in the atmosphere and the amount of heat that is lost to space. So it's this constant fluctuation between the amount of heat that's being trapped in the atmosphere and the amount that's being lost to space. So if you take a look at this diagram, you can sort of see what we're talking about. You've got sunlight coming in, and then you have some of that being absorbed. You have some light being reflected by the Earth's surface. Ice caps are really good at reflecting light, but the absorption of that allows for re-radiation as heat. Again, like I just said, some of that re-radiated heat is going to escape into space, but you have this layer of greenhouse gases in the atmosphere that will do the job, like we said, of trapping some of that energy, and it will push it back down. And so what you have is a trapping of heat in the atmosphere, which regulates the temperature of the Earth and allows us, frankly, to survive. Without the greenhouse effect, Earth would be roughly 30 degrees Celsius cooler than it is today. And I know you guys are used to Fahrenheit, so I'll let you do the calculations yourself to determine what that would be in Fahrenheit. But 30 degrees Celsius cooler without the greenhouse effect. So that greatly impacts our ability to survive here on the Earth. Okay. So what about that other part, that unequal distribution of heat? Well, if you take a look at the Earth, you will notice that it is on an axis. Okay, it is tilted, and it is tilted roughly 23.5 degrees. And so because of that tilt, that solar radiation coming in from the sun is going to strike the surface at an angle. And because of the tilt, that angle is going to vary from one latitude to the next. So where do you think might get the most sun? Great job, at the equator. So at the equator, the angle is the most direct, meaning it's going to absorb the most sunlight. Compared to the poles, which have a greater angle, so more light is going to be reflected and less is going to be absorbed as heat. Paired along with that is the fact that the Earth's surface is curved. I'm sorry to break some of your guys' bubbles, but the Earth is not flat, it is curved. And so because of this curvature, the same amount of energy is spread farther at the poles than it would have been at the equator. So let's say we take a fixed amount of sunlight and we shine that amount of sunlight on the poles, and then we shine the same amount of sunlight on the equator. What we're saying is that that same amount of sunlight is going to be spread out farther at the poles than it would be at the equator because of the curve. So at the equator, it's a higher concentration of sunlight, meaning it will have a higher temperature. That's all we're saying with that second part. So because of the axis, solar radiation is going to strike at angles, and because of the curve, the same amount of energy is spread out farther at the poles than it would be at the equator. Those two things result in warmer temperatures at the equator and cooler temperatures at the poles. So here's a diagram to sort of talk about or show what I'm talking about. So you have the most direct sunlight coming in at the equator, which creates this band that we call the tropics, and that is from the equator, north and south of the equator, 23 degrees or 23.5 degrees to mimic the tilt of the Earth. Okay. If you've heard of the Tropic of Cancer and the Tropic of Capricorn, those are the two tropic lines that designate the edge of the tropics. Okay. Then you have a band of temperate north, and you have a band of temperate zone south of the equator, between 23.5 and 66.5 degrees, both north and south of the equator. We live in a temperate zone. And then finally, above 66 or below 66.5, you have the polar zones. So you have the North Pole and the South Pole. So how do those things give rise to these global wind patterns I mentioned earlier? I just got done talking about heat, but ultimately it's wind and ocean currents as well that are going to determine our climates. So let's talk about wind. What happens to air in those warm areas such as the equator? So we just talked about there's a lot more heat energy, there's a lot more energy from the sun in those areas. What's going to happen to the air in those places? Well, what do we know about warm air? Hopefully you know that warm air rises. And as warm air rises, it's going to become less dense, it's going to spread out. And as it rises, it's going to move either north or south, depending on where it's at. And as it rises, it's going to decrease in temperature. So you have this warm air near the surface, and it's going to rise. And as it rises, it's going to cool off, and it's going to spread out. And it's going to fall back down once it hits a certain degree of coolness, per se. And it's going to return back towards the surface of the Earth, where it will warm up again. Can you see how this might create a cycle? Here's the key to remember, though. It's not dropping back down to the surface in the same place that it rose up from the surface. So you're creating this area of circulation where warm air rises in one place, it moves north or south, and then it drops back down in another location. So you have a movement of air. So the warm and cool air as it rises and falls generates wind. And then if you add in the rotation of the earth, this is what we're going to see cause wind patterns. So in the temperate zones, wind blows typically from west to east. Now, yes, there are days where weather might blow wind from another direction. You might get a blustery cold front from the north. We're talking about prevailing winds is what we're gonna call these. But we have prevailing winds that move from west to east in temperate zones and from east to west in tropical and polar zones. And I've got a diagram here on the next page to show you what I'm talking about. So here's exactly what I mean by that. In the equator, here's that warm air rising near the equator, and it's going to move north in this case. As it cools, it's going to fall back down, and you're going to create this cell or this circulating air pattern. You've got that happening in multiple locations north and south of the equator. You've got several cells. There are 3 cells to the north and 3 cells to the south of the equator. So, back to what we were talking about with wind, though. Because of the rotation of the earth and the movement of this air, you can see the air is moving in this way, so the wind is going to blow in that direction. And the air is moving in this way, so the wind is going to move in the opposite direction. And so what you have are what we call the polar easterlies and the westerlies and the north trade winds. And don't worry, guys, you don't have to memorize all those, but they have fancy names for them. But you should know that in temperate zones, you see a general prevailing wind from west to east, and in tropical zones, you see a prevailing wind from east to west. Same with polar, east to west. Okay, so that brings us to ocean currents. And the nice thing about ocean currents is that they function very similarly to wind, except for there's one big hiccup with ocean currents, and that's that continents are in the way. Okay, so wind gets this nice easy job of blowing over top in the atmosphere. Oceans bump into continents as they go, so they have a little bit more, so they're not quite as straightforward. But what you should understand about ocean currents is that they work very similarly in that warm and cool air, wind, all have an impact, but then again, like I said, so do continental locations. And what you'll see, guys, is that the influence of the air temperature, so where you're at with the wind, and the surface temperature of the water, so the ocean currents, those are going to interact with each other. And they're not only going to have an impact for organisms living in the ocean, but they're also going to influence the climate and weather in coastal areas. And so what I mean by that is take, for example, like Oregon. Oregon and Washington border the North Pacific Ocean, where they have cold surface currents. If I scroll back to that picture, you're looking up here, they've got a cool ocean current up here. They've also got prevailing winds that blow from west to east. So take these winds plus this current, and what does that result in for their climate? Well, what you'll see is that any moist air that is in that area is going to hit the mountain range that is right here. And what you will see is that on one side of the mountains, you'll have a lot of rain, you'll have lush valleys, a lot of vegetation, things like that, which if you've ever driven the coast up there, you will have seen that. But on the other side of those mountains, you'll see very little moisture, you'll see warm air that is very, very dry and not much rainfall, maybe like Nevada. Okay, so that's kind of what we're talking about with how these things impact weather and climate. And we are going to pause right there. We will start next time by talking about changes in climate and sort of the ways that humans can possibly cause changes in climate, but also the things that naturally change the climate.